Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X published on February 11th, 2026, just about 6 days ago. It challenges standard machine learning intuition by showing that repeating a tiny dataset of 400 samples for many epochs actually outperforms training on 51,000 unique samples, boosting performance by up to 26 percentage points. The paper is titled, Data Repetition Beats Data Scaling in Long Chain of Thought Supervised Fine-Tuning. And as we'll see later, the implications for reducing data costs while improving reasoning capabilities are really significant. Alright, Figure 1 illustrates where this method fits into the standard training pipeline, specifically zooming in on the supervised fine-tuning stage. The diagram outlines the flow from pre-training down to reinforcement learning on the left. Inside the expanded view, the common approach maximizes dataset size and trains for just a few epochs, typically 2 to 5. In contrast, the authors propose using a small random subset of that data and training for many more epochs, often 20 to 50, which effectively reduces compute by about 8 times. Well, Figure 2 presents the core results for OLMO 37B, broken down by accuracy, pass at n, and termination rate. Each heat map arranges experiments by dataset size on the horizontal axis and number of epochs on the vertical axis. The key takeaway here is the color gradient. Performance consistently improves as we move up and to the left, which corresponds to smaller datasets trained for more epochs. For example, in the accuracy plot, the standard 1 epoch approach at the bottom right scores around 17%. In contrast, repeating a smaller subset for 32 epochs pushes that score to 39%. Finally, the termination rate panel on the right reveals that sufficient repetition is crucial just for getting the model to stop reasoning and produce a final answer. So, while the previous figure visualized the trend for one model, Table 1 confirms the results across OLMO 37B, QN38B, and QN34B under a fixed compute budget. In every section, the top row represents the standard approach, 1 epoch on 51,000 samples. For OLMO 37B, this yields a GPQA score of 11.5. However, looking down at the 16 epoch row, where the model sees only 3,000 samples repeatedly, that score jumps to 34. The Quen models show the exact same behavior, demonstrating that this benefit from repetition is robust across different architectures and sizes. Alright, Figure 4 investigates the relationship between memorization and performance to find a practical stopping point. The 3 panels plot downstream accuracy on the vertical axis against training set token accuracy on the horizontal axis. Points are colored by epoch count, with green dots representing standard single epoch training. As the model repeats the data, performance moves toward the top right, indicating better accuracy as memorization increases. Crucially, these gains plateau once training accuracy nears 100%, which implies that full memorization serves as a reliable signal for when to stop training. Well, Figure 6 addresses a major concern. Does training on such a small, repeated dataset cause the model to forget its general knowledge? The charts compare the two strategies over total update steps. In the top panel, MMLU accuracy, which measures general capabilities, actually drops faster for the standard single epoch approach, shown in green. Meanwhile, the orange line, representing the multi-epoch strategy on just 200 samples, maintains higher general knowledge scores. Crucially, looking at the bottom panel, this repetition drives reasoning accuracy from roughly 15% up to nearly 40%, confirming it is a strictly better trade-off. So, Table 4 validates using memorization as a stopping criterion across all tested models. It tracks performance for OLMO 37B, QN38B, and QN34B as the epoch count increases. In the top section for OLMO, as we scale from 1 to 32 epochs, the token accuracy in the far right column hits 100%. This coincides perfectly with peak performance. Crucially, for the smaller QN34B at the bottom, continuing past this full memorization point actually degrades accuracy, confirming that hitting 100% training accuracy is a clear signal to stop. Wrapping up, 2 takeaways stand out. Deep repetition on small datasets consistently beats shallow training on massive ones for reasoning tasks. This implies fine-tuning teaches the structure of reasoning rather than just new facts. Practically, developers can cut costs by training on just a few hundred examples until full memorization. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.